could introduce somebody. I should introduce Matthew Kale, because this talk is inspired by the talk he gave 2 weeks ago about random graphs and their associated Clique complexes, which after I just said that I'm going to call flag complexes from now on, and calculating the homology of these groups. Now the reason I thought that was interesting was that for years I've been thinking about groups that were defined by a graph, by a certain graph, like right-angled Coxeter groups and right-angled Artin groups, and calculating things about their group cohomology from the homology of the Clique complex. So I realized, what I was doing were calculations of invariance homology of certain random right-angled Coxeter groups and Artin groups. So that's basically the whole talk. But I guess I'll just kill some time with that. So, I'll tell you what I've been calculating, and I'll see if I can say anything about the relationship. So, in fact, today I'm going to use, Matthew used G for a graph, but I might have a group, so I'm going to let omega be a simplicial graph. And
that just means a graph with
where edge is determined by its two endpoints. So there's no loops and no digons. That's what everybody was doing, yeah.
Is that what a simplicial graph is?
It's a one-dimensional simplicial complex.
okay. No cycle.
Okay, boy, I didn't expect to get stuck already with that. And so X is the associated flag complex or Clique complex. Maybe this should be X of omega. So this is what what Matthew talked about. So basic idea was you have some graph, maybe, and there's some place where you have some 3 cycles, and maybe you even have some complete subgraphs on 4 vertices, and basically the associated flag complex is you fill in all the missing simplices. So you fill in all the triangles, and then you fill in all the tetrahedra, etc. So in other words, its simplices are the complete subgraphs. And I think that's a pretty random way. I think that's a pretty good way to make a random simplicial complex out of a random graph. So as Matthew pointed out, a flag, say something is a flag complex, just means it doesn't have any empty simplices. So, for example, the barycentric subdivision of anything always has that property. Okay, and so then the theorem, maybe the first theorem that this was all motivated about was this ErdosRennie Theorem, which we've said several times, which said that, okay, so first of all, I should have said, so he's going to use the notation omega np to mean the random graph on n vertices where the edges are assigned with uniform, with probability p. Probability of an edge is p. So really you mean the probability space, and you're interested about when a graph like that has certain properties. And xnp will mean the same thing for the simplicial complexes. And what these guys proved was that if, say, p as a function of n was something like, well, it was bigger than, this is what Matthew wrote again, log n over n, by which he really meant p was log n plus something that went to infinity over n. So the difference between So if this was true, then with probability 1, as n went to infinity, or they said asymptotically almost always, or AA, the graph was connected. That this is connected. In other words, with probability 1, something in here is connected. And then later I'll remind you what Matthew told us, but then he had theorems about in certain ranges when this X was highly connected, when this Fly complex was connected, and what its first Betti numbers were. But before I do that, let me just tell you what the groups are I have in mind. Right-angled Coxeter groups, right-angled Artin groups. So in fact, both of these are examples of, maybe I just say it slightly more generally than I need, of graph products of groups. And so this says, so suppose I have a graph on n plus 1 vertices on with vertices, vertex set, say 0 to n, and for each vertex I have a group, and I have a set of groups, a family of groups. In reality, I don't know how to pick them. We'll probably always have them be the same group. Then the graph product, which I'll call G, is you take the free product of these and you divide by the normal subgroup generated by commutators, normally generated by commutators of the form, say Gi and Gj. So an element in the where this is in G sub I and that's in G sub j, you make them commute if and only if ij is an edge. So the graph tells you, so basically you just take the free product of these things and then you make two factors commute by the edges determined by the graph. So the two examples of that, things over here, two really. Three maybe. So, for example, if all GIs are infinite cyclic, then you get what's called a right-angled Artin group. And nowadays, people often write right-angled Artin group, or RAG. And maybe I'll just call that, instead of G, I'll call that A, and it depends on omega. Yeah, maybe I mentioned now, so you could talk about random right-angled Artin groups. You know, for a given graph, you could take A, omega, and P. Maybe I'll just call that the random right-angled Artin group, and study properties of that. In fact, once I told this to Matthew, he showed me a preprint that Michael Farber and Costa had written on exactly this subject. They're not going to, I'm going to say complete different. They calculated like basically their calculation was the dimension of this complex, but it was related to that. Okay, so, and the other case I'm interested in is where all the GIs are cyclic of order 2, in which case you have a right-angled Coxeter group, okay? It is a Coxeter group. It's basically the Coxeter group where you make all the Mij's in either to be 2 or infinity, depending whether there's an edge there or not. And I'll call that W omega. So this, in other words, it has one generator for each vertex. The square of each generator is trivial, and two things commute just as before. Okay, now, so in fact, I'm going to now, I think next thing I want to do is just tell you, oh, okay, no. Before I tell you what, so one of the things I've been interested in calculating, so in general, if we have a group G, you might want to calculate, so I'm going to tell you, I'm going to talk about formulas for the cohomology of G with coefficients in the group ring. Now, what does this mean? So in general, this means that, for example, if the geometric meaning of this is if G acts on a CW complex Y, which is, say, properly, maybe for this statement, co-compactly,
This is equivalent.
ZG,
There's an action of
Z,
ZG. Are you acting it or no?
yeah, ZG is a G module. It's, in fact, it's a ZG bimodule. So in fact, right. This is, yeah, if you like, it's the cohomology of the KG1 with local coefficients in ZG. But if it's, and if this is contractible, all I wanted to say is that the meaning of this is that it's, if you like, it's the cohomology. So you think of this as the universal cover of a K pi 1 or something. It's the compactly supported. So the key is I'm saying these ZGs just mean finite linear combinations of elements in G, and that translates into this just being the compactly supported cohomology of this contractible space on which G acts with, say, finite stabilizers. That's how these calculations are done. Now, so let me just say, why would you want to study this thing? Well, so here are the reasons why you want to study it. So the first reason is, the classical reason is that this tells you the number of ends of a group. So this is a old invariant of the group, and this is basically the rank of the first cohomology group of this G with ZG coefficients, maybe plus 1. So it's one end means that this is 0. So the number of ends, another way to say that is you look at the Cayley graph and you look at complements of compact subsets, and you see how many components you have and how many components persist as you take larger and larger compact subsets, the inverse limit. And the famous theorem is a group either has 0, 1, 2, or infinitely many ends. And you can say something about it in each of these cases. So anyway.
That's a theorem for any group, not just
Yeah, this is, I think this is true for any group, right? Maybe finitely generated, I don't know. I'm not sure. I'm sure, probably need finitely generated.
Is the statement about just the number of ends being 0, 1, 2, or infinity, is that true for all groups? Or?
Yeah.
Who proved it?
What? So that's Hopf, Heinz Hopf,
Wow.
right? No, that's Heinz Hopf, and then Stallings proved, and Hopf also proved that if it had 2 ends, it was virtually infinite cyclic, so it's infinite cyclic up to a subgroup of finite index. And the famous theorem of Stallings was he proved that if it had infinitely many ends, then it split as an amalgamated product over a finite subgroup. So that's the theory of ends. Now, the other reason you have is if you have some finiteness hypothesis like this, or at least finite dimensionality hypothesis. So let me say, suppose G is torsion-free, or has a torsion-free subgroup of finite index, which has a k pi 1. So something like this is true. Then the VC, the virtual cohomological dimension of G, which means the cohomological dimension of this torsion-free subgroup, is equal to the maximum of the maximal degree in which any one of these homology groups is not 0. And the third thing I wanted to say, so those are two interesting properties of these homology groups. This is cohomology. The third one, which I thought was, so basically I thought I was going to say something about this third property until last night, in which case I realized what I was going to say was probably wrong. But I could still, so the third property, which comes up in this context, is this is more or less a definition. Now, this is a theorem. If the group, so virtual cohomological dimension means you can, one definition in terms of the length of a projective resolution. And so it means the highest dimension in which any cohomology can occur. But you just have to look at the cohomology with free coefficients if you have some finiteness hypothesis. And virtual means you just can pass to a subgroup of finite index. Otherwise, it would be infinite if it had torsion. And the third property is, again, with the same hypothesis, I guess. This is really more or less a definition, but you say G is a duality group or a virtual duality group if of, say dimension m, or degree m, if the cohomology is concentrated in degree m and is torsion-free. So this comes from and is a torsion-free abelian group. So this comes from the case of Poincare duality. We're saying a group satisfies Poincare duality, which is conjecturally the same as being the fundamental group of a k pi 1 manifold. That's supposed to happen when this just is isomorphic to Z in dimension m. But that implies some type of duality between homology and cohomology in general. Even before I say what Matthew said, so, now I want to say, I'm going to go over to these two boards. Now I want to write down what my calculations were. So maybe I'll just say two theorems. So the first theorem will be for Coxeter groups. So let's say W is equal to W of omega. And actually, this theorem works for the graph. Basically, the same result is going to work for any graph product of finite groups, but I just take them to be Z2 for a shorthand.
So this is right-angled Coxeter.
Yeah, say this is a right-angled Coxeter group. Although the way I'm going to write down the theorem, it's also true for Coxeter groups, because I'm not going to define everything. Okay, what? No, it's not. Artin group is going to be theorem 2. This theorem says that the cohomology that I'm interested in is a direct sum over simplices, this is x, or maybe you call it omega, I guess, over simplices in this flag complex. So S of x is just this set of simplices, set of cliques, if you like, and including the empty clique. That's important. Of the following thing, the ordinary cohomology of, I'm going to write the cone, C of x means the cone on x, and then this says x minus the simplex sigma. Tensor, some big free abelian, some pre-abelian group, usually infinitely generated, depending on sigma. Which I won't say anything more about for that. That varies. That pre-abelian group varies. So, and C of x, so this is the theorem, and C of x means the cone on x. So this is basically just in some sense, it's just a device for shifting the degree, okay? So I'm saying, so in fact, the things I'm interested in here, the cone on x comma x minus sigma just means the reduced cohomology of x minus sigma, shifted by 1. Okay? And in particular, when sigma is equal to the empty set, you're just getting the cohomology of x, okay? Which is what Matthew told us about. What?
What's x?
X is this Fly complex, the Fly complex associated to the graph.
So a sum over simplices of x, of the cone on x. Now that doesn't depend on the
The cone on x is just a way to say something contractible, and then comma x minus x. This is no, yeah, it's like suspending this. And then this is x minus this closed simplex. Okay, so for example, if you just had a graph, it says you have to, so this is partly where I got confused. If you just have a graph, it says you have to not only look at the first homology of the graph, you have to look at the zeroth homology of the graph. In other words, whether it's connected, you have to omit points and omit edges, okay, and see if it's still connected. You have to see if they're cut points or edges, okay? And I think it's worse than that, actually. Now the theorem, so in theorem 2, which is for Artin groups, and there's a similar version for graph products of where all the factors are infinite. So this is a RAG, and it says that the cohomology, so that W depended on, so the cohomology of this A with coefficients in the group ring is, again, the direct sum over, well, maybe I'll write it like, I'm just going to write it slightly different. So here there's some dimension shifting going on. So I'll write in dimension star plus m, and I'm going to, again, so I want to get it shifted by m, I'll say, well, let me just say in dimension I plus m, I don't know whether I want to sum over I2, but it's the summation over simplices where the dimension of the simplex is m minus 1. I think maybe I just want to use absolute value of sigma to mean the dimension of sigma plus 1. Okay, and then what you have here is the cohomology of, all right, the cone over the link of sigma, comma, the link of sigma. So the link of so sigma, the link of sigma. It's a similar thing to what it's the cone over something, comma, the link. So the link of sigma means if you have a simplex, you look at the vertices which are adjacent to all its vertices, and you take the full subcomplex spanned by those.
Is this for any m, or are you going to tell us some particular m?
No, or m is the dimension. You just do the sum over.
Gotcha. Yeah.
So I should have said, yeah, dimension I.
In the first theorem, there was a tensor free abelian.
Yeah, there's tensor, and there's one here too.
And so that's tensor over the integers.
Yeah,
And so are you going to tell us the rank of that free abelian?
it's used almost always infinite. Sometimes it can be z. That's one of the. That's a. If I have time to get to talking about L2, that's the advantage of L2 is you can sometimes put a number on those things. But yeah, these groups. Well, in this case, it always will be infinite rank. Maybe one, and unless it's z to the n or something. And in this, it's almost always infinite rank.
Do you mean almost
But
always in a probability way?
No. For the only time it comes out here is when is if you have a complete graph here, then you can get a z in the top dimension, and in this case, if you have a triangulation of a sphere, or but
The dimension minus.
the dimension of sigma.
Vertices that are in
Yeah, yeah. So you shift up the stuff in the link. So in particular, the other thing, so one case here again is where you don't have any shifting, is where sigma is the empty set and m is equal to 0. So sigma equals the empty set and m equals 0 gives you one term here, which looks like h1 of the cone on x comma x minus sigma, which was similar to what we were getting before. Okay, and in other words, h1 of this with 0 shifting. So this is what h1 of a, za coefficients is equal to. Okay, so so the corollary we get out of this ErdosRennie result is that in their regime is if p is bigger than log n over n, then the only way we can get this shifting always takes us up above dimension m unless we're for the empty set, or unless the whole thing was a point. But this says that if p is bigger in their regime, we know that omega is connected. Therefore, the phi complex is connected, and so we get then. So this wasn't stated by Coxeter and Farber. Then a omega, or say a n p, which means the random right-angled Artin group, probability p, has one end. Now let me say what the end. I was thinking for a while I could say the same thing for Coxeter groups, but then I decided I can't. Maybe I'll wait. Before I say that, let me go back and say what Matthew told us, what was in his thesis. So these were well, maybe not the first thing. So here are results of his. The first is that the dimension of this phi complex, this random phi complex, well, I think it's approximate. It's known exactly, but it's very close to minus 2 log n over log p. Then there's some other terms which are log and the constant maybe. So it's pretty close to that. Yeah, this is a point I didn't get before.
So dimension
Yes. Exactly. You're on the right track here. The maximum dimension of a simplex. Now, on the other hand, what he also told us was that in certain regimes, the Betti numbers of this were concentrated. And so basically, it said this. He said that if you had a number between 1 over k and between minus 1 over k and minus 1 over k plus 1, and p was equal to n to the alpha, so n, it's 1 over n to that root, then basically the result was that h star of xnp, he had was concentrated in dimension k, in degree k. Now he had some, actually he wasn't, he had some, I think he has some variations of this. Really, to make sure it's 0 every place else, you have to say that you want to replace this by 2k plus 1. In other words, you want to say that alpha has to be bigger than 1 over 2k plus 1 to really make sure this was 0. But this was enough. This basically said that in this regime, these Betti numbers were basically, the expected value of the Betti number was basically the same as the expected value of the number of k simplices. And
That's a Clique number, isn't it?
what?
That's the same as the size of the largest Clique in the original.
No. This is the point. I should say this now. A k simplex means a clique, right? But maybe we should do this calculation, or if you let n be, if you let p be something like n to the minus 1, if you let p be n, that, which you think of as, say, being n to the minus 1 over k, and you plug it into here, you get, so if p is in this regime, you get that the dimension of x and p is basically is 2k plus or minus epsilon, plus or minus 1. It's basically 2k. Okay. So this was what I was confused about before I started realizing, thinking last night. It's saying the homology, this is the it says the homology is concentrated in degree k, but the dimension of the complex tends to be twice the dimension. It's like concentrated in the middle dimension. And so the picture, isn't that right?
Yeah, that's right.
Right. Yeah, I was confused when we were talking about before. So the picture is that we have what they were calling these, naked simplices. So you should think of it, if k was equal to 1, you should think of it as a picture of you have this graph, and then you have some 2 or 3 dimensional simplices just hanging off of it like that, okay? Naked 2 simplex, that's what you wanted to call that, okay? So, and these are what are going to, okay. So these things can cause problems. So first of all, the way he was getting this cohomological dimension of this art, so in other words, the dimension of the top dimension of the simplex is not the dimension of this graph. It's twice it. On the other hand, these things, when I had these terms involving the links, sort of a naked simplex can definitely contribute. In fact, if you take a maximal simplex, its link is the empty set. And the thing that we'd be, so in other words, if sigma is a maximal simplex, then the link of sigma is the empty set, and the cone on the link of sigma is a point, okay? So you get H0. And then it gets shifted up by the dimension of that plus 1. That was actually what Farber's calculation was calculating the dimension of these maximal simplices. And even if it's not a maximal simplex, you have problems with if you take something like you take something like this. Here's a one-dimensional simplex. Its link is again. Well, that doesn't cause a problem. Well, its link is a point, so that wouldn't contribute. But anyway, these maximal ones contribute. It might, I mean, if you had something like that, if it was covered on both sides, then the link would be a zero sphere, and that would contribute. But the maximal ones are always going to cause me trouble. So, I mean, what I had thought, what I would just, random thinking, I thought I had this feeling, I thought we could say, okay, so the other thing that Matthew told me was that if you look at the link, maybe I'll just make this point. So this is one, if you look at the link of a simplex on so many vertices, inside this random flag complex, it's basically, it's another, you get a random, it's a flag complex on another random graph. So where what happens is that you just have to look at, so you have this has, say m vertices, and each of those has probability. You want to say, you want to look at the vertices in the link, so you want to say when does a vertex connected to all the vertices in these, so each one has probability p, so it's p to the number of vertices times n, okay? So this link is this random graph where we replace n by p to the cardinality of sigma. Now that means, if you think about what happens with this shifting, that means that that basically has the effect of, if you start out with alpha in here, when you look at the link of a vertex, these two limits get shifted down by 1. That goes all the way up to the middle dimension, but when we get when we get up to the number of elements here is k, this has become approximately 1. Okay, so you're taking something like the random graph on one vertex, or on some finite number, some small number of vertices. And so, so what I want to, so my mistake was I thought that this fact was saying that these other terms with the links were also contributing in the same degree, okay? And that's true up through dimension k, but it's not true above the middle dimension. So I don't know if I'll say this is a conjecture for the Artin groups. And then, so for Artin groups, I mean, I think this is probably right. I'm just not sure enough with the numbers yet. So, is that if again, so if p is this n to the alpha, where alpha is between minus 1 over k and 1, then I'd like to say that the cohomology of the random Artin group is concentrated in degrees between k and 2k. I might be off there by 1 or something. It's concentrated in degrees between k and 2k. So what's definitely happening is that these, so where was this? Is that, for example, these maximal simplices, which will occur in dimension 2k, can be contributing something in dimension 2k.
You just mean ordinary integral coefficients at this point?
Yeah.
No group ring.
Oh no, group ring. The same thing. This is like the cohomology at infinity. What I was before yesterday, I was going to say I thought it was going to say it was a duality group, but that was my mistake. I'm confessing to the mistakes. Okay. So maybe this is a mistake too. Now for Coxeter groups, you also have to worry about. Oh yeah, that was where you have to worry about these next to top simplices. So for a while, I thought, I didn't have any good reason for this, but I thought it should be true. I mean, it's true if you have, if you have something like a sphere or something where the homology is concentrated in the top dimension, that you expect, that if you remove a simplex, you shouldn't affect the connectivity of it at all, okay? But now when you think about these kind of examples, like just take this example of this graph with this two thing, sitting on it. Well, you certainly affect it. Oh yeah, even whether you disconnect the graph or not, if you just remove this edge, then the complement is, well, the rest of the graph together with that point. Okay, that counts. Okay. So in other words, and in fact, if you had something like this, if you had a Coxeter, right-angled Coxeter group like this, it wouldn't have one end. And the reason would be because when we remove this thing, we got two components, and it's saying somehow this edge corresponds to a Z2 cross Z2, and it's saying that this whole group splits as something over a Z2 cross Z2 with 3 copies of Z. It splits as a free product over a finite group, non-trivial. So in fact, so the formula was different for Coxeter groups, and it's screwing me up in a slightly different way in that these bigger dimensional simplices, I don't think that they're affecting, there's no shift, but when I remove them, I still can be affecting the lower dimensional cohomology. So the conjecture I would make for Coxeter groups is that they only affect the lower dimensional stuff. So in other words, if P in the same range, if P is that, then I'd like to say that the cohomology of a random Coxeter group with group ring coefficients, well, is concentrated in degrees less than k, or another way to say that is just to say that the virtual cohomological dimension of a random Coxeter group should be k. This is where alpha is in that same regime as above. So all the cohomology is less than k. Okay, so in fact I do have time to vary this up to L2 cohomology now. I mean, I probably left out some things. But let me make a, so this I'm not going to have any conjectures in what's left, but I'm going to have some other things, some other numbers which deserve to be calculated for random Coxeter groups and Artin groups. And actually, this is going to be interesting when we're taking graph products of, say, groups, each of which has some finite order, like order q, or q plus 1. But first of all, let me just say something about L2 Betti numbers. So I think I'm going to end up lying here, but so and I don't even know if I'm going to be using the right notation. But so G is some countable group. Maybe I have L2 of G means the square summable functions on G. So in other words, it's just the, it's just like the same as things in the group ring, AG or XG times G, where this is an infinite sum, but the summation of the coefficients is converges. That's what L2 of G is. And now I'm going to write something, maybe I'll put a script, a H star of G with L2G. Coefficients, this is what I mean by, I have to explain what reduced means. Reduced L2 cohomology. So if you like, if I didn't have the reduced here, this should just mean something like the cohomology of the universal of BG, equivariant cohomology of that with coefficients in L2 of G, or if you like, when I have G acting on this Y, contractible Y, it's basically just the cohomology of this universal cover. Maybe I should put a G there with L2 coefficients, with coefficients in L2 of G. But you want to make this into a Hilbert space. That's where this word reduce comes in. So in fact, this isn't exactly the right thing. This is just completely minor. I mean, from our point of view, you find this is the kernel of the co-boundary divided by the image of this closure of the image of the co-boundary, just in order to make it a Hilbert space. So you take some closure of the co-boundaries to make that into a Hilbert space. And then it turns out that using this group action, you can define, you can take a trace and define, so if we have a closed subspace in some number of copies of this, some direct sum of these things, then we can define the dimension of this subspace, as this is closed, G invariant. You can define its dimension by taking the trace of a projection onto P. And this is some number, some positive real number. And it has the good properties of the dimension. So using that, you can define the dimension of you can define the dimension of these things, and they're called the L2 Betti numbers. So I'll say beta k, maybe if I remember to put a 2 there, is this dimension over G of this L of this thing. So those are. So again, these things are usually, as vector spaces, real vector spaces, they're infinite dimensional, but we can define this real number associated to it. And for example, one of the things you can do, which we like to do, is you can find the L2 Euler characteristic of this group G.
These are really, this can be this can be the square root of 2 or something?
Well, when you have torsion, so yeah, as a general, for a group, that was the Satia conjecture, that it couldn't be the square root of 2. It said if you built something, if you had a universal cover of a finite k pi 1 or a finite complex, all the Betti numbers had to be rational numbers. Okay, that was the Atiyah conjecture, which is in some more generality where we have these infinitely generated lamplighter group type things, or infinitely presented. It's false. Okay. it's now, there's counterexamples to that, maybe not in the tight generality I said. But if you just say, when can these dimensions be a real number? They can definitely be the square root of 2. They can be any real number. That's easy, just for Z. It just, yeah, it's completely simple. It was due to von Neumann. Yeah, so Atiyah partly was led to this conjecture because in the standard case, this Euler characteristic did come out to be a rational number. And what he said was, if you define this to be the alternating sums, I'm going to just of these beta k's, that turns out to be basically the ordinary Euler characteristic of the quotient space downstairs. Now, if there's torsion, you have to weight the cells downstairs by their order, so it's the orbifold Euler characteristic. Anyway, so it's a more well-defined thing. Now, okay. Okay, so now I want to tell you what this is and what the answer is for graph products of finite groups. And so first thing I want to say, so one thing I want to say is I want to talk, what comes up in this is what's called the growth series of a Coxeter group. So by definition, this is the power series, say W of t, which is just the summation of t to the length of w over w, where this is with the standard set of generators. And it turned out, it's proved in Bourbaki's book on Coxeter groups, that this power series is a rational function. And in fact, they give various explicit forms for it as a rational function. And the nicest one is this. One of the nicest ones is this. It's not a form for this, it's the formula for 1 over this power series. For 1 over Wt, it says it's the summation over simplices in this same flag complex of I'll just write it like this, minus t divided by 1 plus t to the dimension of the simplex, okay? And in fact, people in combinatorics, if you think about this for a while, this is basically the definition of what's called, I mean, you can almost take this as a definition of what's called the H polynomial of x. This is more or less by definition, it's the H polynomial associated to this phi complex x at minus t divided by 1 plus t to the dimension of x. This H polynomial is something which is another way to encode the number of simplices in the complex. Its coefficients are certain linear combinations of those. And that's what it is. Okay, which one do I, maybe I'll save that one. So now, so for the, so actually, so so now what I want to talk about is, I now want to allow myself to take each of these groups. I want to take G to be this graph product of GIs, or say graph product of Z mod Q plus 1, or any group of order Q plus 1. Okay, Q is the number we like. Okay, and then okay, so the first theorem says this is graph product. I mean, the first result is that if I take this L2 Euler characteristic of this graph product, the alternate, which is some ordinary Euler characteristic, this is in fact equal to 1 over this growth series evaluated at q. Okay, so in other words, it's this h of minus q divided by 1 plus q to that dimension. So it's completely explicit. Now, okay, now what turns out is that
So that's the other character. So you told us what Betti numbers are. You take their alternating.
I told you the definition. I haven't told you what the answer is for those, okay? There isn't, I mean, I told you that the Betti number is just defined as L2 Betti number. I don't know how to compute those yet.
Wait, this chi k is the alternating sum of.
It's the alternating sum of Betti numbers, okay?
As defined up here.
As defined up here. But in fact, the proof of this is you can also take it as the alternating sum on the chain level of orbits of cells, and then it's just counting cells. Right. Now, so in fact, what happens is that we don't completely, so the situation is this: for a general Coxeter group, I don't know how to compute these. For a right-angled Coxeter group, we don't know the answer. When q equals 1, that corresponds to, that means right-angled Coxeter group, and we don't know the answer. We don't know the answer. But in a certain range, for q large enough, we do know the answer. And what the range for q is, if q is bigger than 1 over, either say 1 over the smallest root of the h polynomial, which in other words is also known as 1 over the radius of convergence of the growth series. If the number q is bigger than that, the smallest root is a number less than 1, so 1 over it is a number bigger than 1, then you know the answer. And this is the answer. Maybe theorem 3. So if q is bigger than this 1 over this, I usually call it rho, this number rho, then the answer is very similar. This g omega, how should I write this? So it's L2 Betti number, which depends on q, is again equal to the sum over the simplices, and then you take this ordinary Betti number, ordinary dimension of that cohomology group. So you take, let me just say, call it the ordinary dimension of the cone on x, comma x minus sigma. That's the ordinary Betti number, and then it's times some explicit rational function times, I'll just write h sigma of q, where h sigma of q is, it's a formula like the formula I gave you for the growth series. It's closely related to, well, it's in our paper, but it's basically a formula like this, except where you sum over the simplices in the link, or the star. You sum over all the simplices which contain this, something like that, and maybe you plug in q inverse instead of q. Okay, but it's, so this is some completely, this is some explicit rational function. And actually, the way we did this was in the paper I wrote with Damar, Januszkiewicz, and Oken, which was called Weighted L2 Cohomology of Coxeter Groups. It turned out that these could be interpreted as some sort of cohomology of the Coxeter group with respect to a Hecke algebra for Q. And in fact, the interesting thing about that was that Q didn't have to, and here Q is the order of a finite group, but in these formulas, it made sense for any positive number Q.
So Q is the order of which finite group?
So I was taking the graph product. Well, it doesn't, any finite group of order Q plus 1 is the order of the finite group. I have formulas that would have a series in different variables for any graph product of finite groups, but just to make it one variable, make them all the same finite group and make it order Q plus 1. Okay.
You must have said what row is.
I did, row, I meant the smallest root. Okay, perfect timing, expert planning. Ready?
Are there any questions for our speaker?
The first pair of theorems you had over there, the ones not about L2 cohomology, those must have been a certain space is homotopy equivalent to a.
It's actually different papers, yeah, but okay, so in reality, so the first theorem I proved was this theorem 1,
Right.
okay, and it was my usual construction I've been doing for years and years. I just didn't like to say it again. But you make this nice space that W acts on with co-compactly, and the fundamental chamber is basically the cone on X, okay? And then you prove it's contractible by gluing on one chamber at a time, and to figure out what this is, you're sort of figuring out what it is in infinity, and this is measuring. It turns out you basically always glue things on along a contractible piece, basically along a neighborhood of this simplex, a regular neighborhood of this simplex. And so this is the stuff where you glue on some chamber and you don't glue it onto, this is where the part where you don't glue it onto the previous stuff. And it ends up contributing to the stuff at infinity. So that was a proof from, I forget when, 20 years ago maybe, I had some argument like that. And then I should have said the theorem 2, actually some of this is fairly recent. The theorem 2 for Artin groups, I should have really attributed that to Craig Jensen and John Meyer, although their proof, they had a proof using theorem 1, okay? They had the Artin group was commensurable, was finite index in some bigger right-angled Coxeter group that you got by doing some doubling construction to this graph, and then they used this theorem to figure it out was for the Artin group. And but the recent business about graph products in general, and a new proof of that theorem 2 is Boris Oken, and I have a new paper which is on the archives called Cohomology of Artin groups and graph products or something like that, which is some spectral sequence argument.
Actually, I have a question for Matt. So you gave us a whole bunch of intuitive arguments when you gave your talk, but do you have, is there some direct way of seeing that the cohomology of these complexes is half the dimension of the complex, or is it just two separate calculations of the cohomology dimension?
The dimension of the complex is really straightforward, and that shouldn't be attributed to me. That's just the size of the largest clique in the random graph, and that's well known to random graph people. That's something you can look up in Bolobasch's book, just whether or not a subgraph is contained in this random graph or not. It depends on the subgraph and depends on P. So that's a very easy calculation. Why? So if then you can set P to be a function of n, a right power of n, like Mike was saying, so that you can fix the dimension then of the clique complex for that reason. If it's d-dimensional, it turns out homology all vanishes above dimension d over 2. And there's a lot of homology in dimension d over 2. It's very easy to see that there's a lot of homology in dimension d over 2. One argument is that just the f vector makes it so there's so many more faces dimension k, that there are k minus 1 dimensional faces or k plus 4 dimensional faces. It just dimension argument tells you that there's a lot of homology in that degree, but it's a lot more subtle argument to rule out homology above that dimension.
But you don't have a plausibility argument for why it's exactly half the dimension, as opposed to say a
Above
third
that or
dimension.
below?
Other than, I mean, there has to be something in, it can't be a third dimension because there has to be homology in dimension d over 2. So that's sort of the smallest the cohomological dimension could be is dimension d over 2, but it just turns out that is the right answer. So by the way, I'm working hard now on showing that there's no other homology except in the middle dimension. So we just got to rule out that the bit between d over 4 and d over 2.
All right, let's thank our speaker again.